Thank you for the kind introduction, Chairman. And also thank you for the organizers for inviting me. And then today, I'm going to talk about the order parity electronic multipole ordering in uranium-ruthenium-2 silicon. My name is Hisatomo Harima from Kobe University, and also I am the area representative of the project in J-physics in Japan. And then this is the paper we wrote 8 years ago. And then my talk is based on this paper, but I correct one thing of this paper. And also I should ask many people that Professor Amitsuka and I, we have a lot of discussion, and also the Kusunose-san. And the important experiment today I introduced is done by Mito. He measured the ruthenium NQR measurement, and also the Shinkanbe, he measured the silicon NMR in uranium silicon 2. And I briefly introduced the Raman scattering done by in French group. And this slide is prepared by Professor Kusunose. He will talk on Thursday and about the multipoles. And then we know there's many kinds of multipole. The example, the electric even parity multipole, electric monopole, and magnetic dipole, and also sometimes we discuss about the electric quadrupole and the magnetic octapole. And then we call them the conventional multipole, defined in the single orbital at the single site. Then all of them are even parity. But recently we extended the definition of the multipole, that we say the augmented multipoles. And then the augmented multipole is divided into two classes. The one is cluster multipole, defined in the multi site. And the other one is hybrid multipole, defined in the multi the orbitals. Then, by using these as a multipole, we are trying to explain the variety of the physical properties. Today, I'm going to talk about this hybrid multipole, defined by the multi-orbit. Then we can have the order parity multipole, electric dipole, and also the electric octapole. But in the uranium-ruthenium-2 silicon 2, this is a very special case. We should introduce the rank 5, the Dottria quantapole, electric the rank 5 Dottria quantapole. Then I talk about the hidden order in uranium-ruthenium silicon 2. This hidden order is very famous, but some of them don't know that very much. Then this is the crystal structure of uranium-ruthenium silicon 2. The uranium and the ruthenium and the silicon here. And then this is the specific heat over T versus the temperature. At around 17 Kelvin, there's a big jump in the specific heat. And then in low temperature, it goes superconductivity. But I'm not going to discuss about this superconductivity. Just discuss about this as a phase transition. Then this is a temperature pressure phase diagram. At applied pressure, there's a large magnetic moment, antiferromagnetic ordering. Then this is called the hidden order. This is this corresponding to this big jump of as a space heat. And this is superconductivity. Then this transition here is a second order phase transition. And then the other parameter of the phase below T0 is still unknown, because any structural distortion have not been reported, and the low pressure hidden order phase is not magnetic origin. And then as a consensus at the time in the 8 years ago, there's a consensus of the measurement in the hidden order. Then this is written by Professor Amitsuka. And then the second order phase transition plus, and then there's no uniform lattice distortion from tetragram within the 10 to the minus 6 accuracy of the high resolution X-ray and the thermal expansion measurement. And the superlattice selection have never been detected in neutron and X-ray diffraction. And time reversal symmetry appears to be conserved, and no anomaly is detected in the, the ruthenium NQR signal at the T0, hidden order space transition. And then this is the most likely, and this is still as a small anomaly. There's a small anomaly, but still the fourfold symmetry kept. Then this is ruthenium NQR frequencies. In the case of uranium-ruthenium-232, that as a NQR frequency versus temperature, and this is as a hidden order transition temperature, but no anomaly appeared. But as a similar compound, this is also this was called the hidden order state. But in the process of ruthenium for phosphorus 12, and as a frequency versus temperature at around 60 Kelvin, there this the compound shows a metal-in-shear transition, and the NQR frequency shows the anomaly at the 60 Kelvin. Then this is then after in the process of the ruthenium phosphorus X-ray and electron diffraction measurement, and they detected the small change of the atomic position, but very small. But actually, in this case, the atoms are distorted, very small. But in the uranium-ruthenium-232, we don't have such a measurement. And also, this is a result of the thermal expansion. In the uranium-ruthenium-232, and at the hidden order temperature, the thermal expansion is changed, but the order is 10 to the minus 6. And also, the process of the ruthenium-2 phosphorus 12. And also the thermal expansion jumped, but also the order of the 10 to the minus 6. And then there's the very similar. But also this thermal expansion, this is also the evidence of the phase transition. And the 6 feet and the thermal expansion, this is very clear for as a phase transition. But we don't have no other anomaly. Then the other properties. And here, as I said, this is unsure magnetic ordering, like this. It is the by neutron the measurement. It's very clear. And also here, there's a phase transition. If you can apply the pressure, then there's a C over T jump and there's a low jump, also the resistivity jump, but it looks unchanged. The order state and the archimagnetic ordering state. And also there is a first order transition. The topology of the Fermi surface looks unchanged. So we will say the Boolean zone is unchanged from hidden order to the long range magnetic, archimagnetic magnetic ordering. Then we propose the order parameter of the hidden order state 8 years ago in this paper by Professor Miyake and Jack Fulke. And then one simple answer is why the hidden order is still hidden, is presented. Because there is a subgroup, and then in the crystal structure of the subgroup do not couple with the lattice. Then we cannot detect any distortion. Then we discuss again based on this paper. This is a crystal structure. And then the uranium is, the uranium is here, and the ruthenium and the silicon. And then this is the Wyckoff position. Over the MM is the local symmetry. And the ruthenium site for M2 and the silicon site for MM. Then we should look for the subgroups, because this is the second order phase transition. Then we can find the subgroup by using an international table. And here is the maximal subgroups written. Then this is subgroups classified to maximal non-isomorphic subgroup. It is called the T subgroup, and also the K subgroup, and then also the lower index subgroup. And then this type 1 subgroup corresponding to the ferroic order. And because the uranium-232 is a body-centered lattice, but the body-centered lattice is unchanged, but the crystal class is changed. this is distorted, mostly as I lattice, but this is distorted to the lowered to the orthorhombic lattice. And this kind of sublattice is as a I lattice changed to P lattice. But as a crystal class, it's the same as the point group is unchanged. Then this is as a lattice. The lattice constant is it corresponds with the superlattice. Then this is as a then okay, and then this as corresponding to the ferric order, and also this corresponding to the antiferric order, and this corresponding to CDW. Then now we can assume the Q equals 001. That we look for the as a subgroup in this as a K subgroup. Then this is a K subgroup. There are 8 subgroups here, and then the uranium site, ruthenium site, silicon site, the local symmetry is changed, was as a 2 atoms should split. But in the 8th subgroup, there are the 4 subgroups, neither atoms neither move or split. Then we cannot for the 4 subgroups we cannot detect as a change of the phase by using the X-ray, because the atom itself never changed. Then here is a ruthenium site lost the fold symmetry. Then we know from the ruthenium NQL measurement, there's a fold rotational symmetry kept in the hidden order state. Then these 2 the subgroups are eliminated. Then these 2 local symmetry remain. But this 422 breaks the local inversion symmetry. Then in this paper we take this the symmetry. Then because we consider only the 5f electron. Then I conclude the quadrupole ordering in the URuSiz2. But I should say something that these subgroups are symbolic subgroup. Then this is a local symmetry. For example, the 136, the A site was the corner and the center of the uranium site. They are split. They are ordered like this, but they are connected by some symmetry. Because then in that case, these subgroups are belonging to the symbolic subgroup. Then they and also this is these local symmetries break the inversion symmetry. This is the order parity inversion symmetry. But so in the previous paper that we only think that these as a hexadecapole order and the quadrupole order. Then this is the monopole ordering. This is the Dotoriak octapole, dipole, octapole. These are the order parity ordering. But in the previous paper, I didn't think about this. And then this is the character table for the D4H. And then there are 10 irreducible representations. And among them, the 8 single irreducible representations. These 8 single representations corresponding to these subgroups. Then this is the same, but there's an ordering. This quadrupole ordering, it corresponds to the B to Z. And then there's these the ordering corresponding to the Ungerade, the order parity ordering. And this is the basis of the belonging to the irreducible representation. And these the basis also represent the multipole. For example, this B to Z is corresponding to the quadrupole. It's xy, and in this case, x squared to minus y squared. They are quadrupole, but a different type of the quadrupole. Then quadrupole again. And then, in the previous paper, we conclude that antiferrocquadrupole quadrupole ordering from the paramagnetic state to the hidden ordered state, like this. Then this is a ruthenium site, but the ruthenium site keeps the four-fold symmetry. Then we conclude, and this is as an ordered state, and this is a paramagnetic state. But this quadrupole, the ordering has not been detected. So now I think that this is not the solution. And then I compare the other kind of quadrupole ordering, like this, number 131. This is also the quadrupole ordering, but in this case, the ruthenium site split two sites. It's a crystallography different site. Then also the ruthenium site the four-fold local symmetry, but in this case we can detect it by X-ray detection. So this is not the case. Then also we discuss about unchevron hexadecapole ordering, but this is breaking the four-fold rotational symmetry at the ruthenium site. So this is not site. But if we take the ferro ordering, this is also possible. So now we should go back to the K subgroup. Then these four subgroups is not the case because we can believe that X-ray detection. But there are four subgroups remain. And then these two improper four-fold rotational symmetry remain. And these two four-fold symmetry remain. So we can classify the ruthenium site, if the ruthenium site four-fold symmetry kept here. And in the silicon site, if there's a four-fold rotational symmetry, we can take these the subgroups. Then when we check the four-fold rotational symmetry, both ruthenium site and silicon site, we can choose one of them. Then this is a ruthenium NQR measurement by Mito group. And then they measured very carefully. This is an anisotropic parameter because of the nu q and the two nu q. Then they concluded as eta equals 0. And also that they carefully measured the NQR, and then they detected a very small anomaly at the T0, hidden ordered state. But this is consistent with the thermal expansion because the lattice itself is keeping the tetragonal lattice, but the change, the lattice constant. Then they can detect the small anomaly of the NQR measurement, NQR frequency. And then also they measured, and then they measured very carefully. Then they conclude the nu q over 2 nu q over nu q is a 2.000 plus minus 001. Then eta equals 0. It means that the four-fold rotational symmetry is kept at the ruthenium site. And and also the 99 NMR measurement they measured, and then they conclude also that eta equals less than 0.002. But very difficult to show the four-rotational symmetry of silicon site because recently, but this is also the measurement by Professor Mito, and then the germanium is substituted by a silicon site, and then they concluded that eta equals less than 0.05. But this is a very recently the Shinkanbe measures the silicon NMR line width, and then he concluded that he observed the two-fold symmetry, but this is the incoherent part. The coherent part is the four-fold symmetry. Then local four-fold symmetry for the hidden order state, and the distributed two-fold ordering in the hidden order state seems to due to the imperfection of crystal. Then we know that for the both sides, the four-fold rotational symmetry kept. Then solution is 126. Then the 126 is corresponding to the local symmetry, the 422. The 422 is here, and then this is only possible in the hidden order state. Then there's an Anchevero Dotoria counterpole ordering is realized in the hidden order state. In the Raman scattering, and Mario will show the main experiment data, and I should mention one thing. And then the transition can give the A to G excitation detected by Raman. Then there's the first author, Jonathan, confirms the A1U, A2U, B2U, B1U, and EU are possible ground state. Then why the countable not propose it? Because it breaks space inversion symmetry, as I said. Then this is odd parity, hybrid multipole. Then it cannot be made from only the 5F electron. 6 electron needed. There's a multi-orbital which needs. The example is like this. And also very important, and all multiple proposed so far is even parity. Then they can made from the 5F electron. Then this is a statement in our previous paper. Then we should think only about the 5 electron. This is wrong. Then the conclusion is antiferromantic electric deuterium counterpole is the most promising order parameter of the hidden order state. And it looks as a big monster, but as I think this as an antiferromagnetic order state. Local time reversal symmetry lost, but the local space inversion symmetry remains. And 2 uranium sites connected by a time reversal symmetry. Then you should switch as a time reversal symmetry and the space inversion symmetry. Then we can have the hidden order state here. Then the conclusion, the local symmetry is lower like this. Then we should detect we should detect the here. And then some remarks. The G factor observed the Sibnikov-Boltzmann effect in the hidden order state. And then both time reversal and the space inversion symmetry remained. And also the many experimental results for symmetry breaking, but they are very tiny. Easily detect the outcome from the imperfection of the crystal when the real order parameter is not connected with that symmetry. So such a symmetry, the tiny component breaking symmetry is also the evidence of the antiferro electric deuterium counterpole ordering. And this is some attempt. If you try the self-constant LDA band structure calculation was space group 126. This is the result. But this multiple order parameter is nearly 0. Then we should finite they are split. So we need the beyond LDA calculation. Then and this is this is the conclusion. But I should mention that next year, 2019, there's an SKS conference in Yokohama in September, and this is the first announcement, and this is a pamphlet. So if you are interested, please take it. Thank you very much.